Okay, so let's jump into two more examples. You should hopefully try these on your own before you watch me do them. So this example, we've got a fraction. I want to know where it's increasing and decreasing and where we have local maxes and mins. We have to start by finding the derivative so we can find critical numbers. So the derivative here, we need a quotient rule. So we're going to have low d high. So low d high minus high d low over low squared. Okay, we're going to want to go ahead and simplify this so we can find the critical numbers. So I have x squared plus 1 minus 2x squared over x squared plus 1 squared. The numerator becomes 1 minus x squared. And then I can factor that numerator as 1 plus x times 1 minus x. Okay. I notice that that derivative will be 0 if x is plus or minus 1. So plus and minus 1 are going to be critical numbers. The denominator is never 0 here because x squared plus 1 is always positive, so we have no places where the derivative does not exist. So my only critical numbers are plus or minus 1. I'm going to go ahead and do a sign chart here. Again, using -1 and +1 on my sign chart. Those are my critical numbers. Again, label your sign chart with F prime. We'll do sign charts for F double prime eventually, so you need to make sure you're labeling your sign charts. I will take off points if you're not including that information here. Okay, it also helps you remember that everything on this sign chart is based on the derivative, not on the original function. Okay, so now I need to plug in a number smaller than -1 to my derivative. So let's maybe try plugging -2 into my derivative. Again, I'm going to use this factored form. We notice the denominator here is always going to be positive because it's being squared, so it's not going to change our sign. In my numerator, I'm going to have 1 plus -2, that's going to be negative, and then I'm going to have 1 minus -2, that's going to be positive. So negative times positive divided by positive is a negative. Okay, I'm going to pick a number between -1 and 1. 0 is a good choice. So if I plug 0 into my derivative, again, the denominator will be positive. In my numerator, 1 plus 0 is 1. Oh, it's positive. It doesn't really matter that it's 1. It just matters that it's positive. 1 minus 0 is also positive. So this is going to be positive for that sign. And then one last sign to figure out, something bigger than 1. Let's plug in 2 to the derivative. Denominator, again, still going to be positive. 1 plus 2 is positive. 1 minus 2 is negative. So my overall sign here will be negative. Okay, so what this means is that f is increasing on the interval from -1 to 1 because that's where the derivative is positive, since f prime is positive, and f is decreasing on -infinity to -1 and 1 to infinity, since f prime is negative. Okay, and then let's see. At those critical numbers, what kinds of, do I have local maxes or mins? Let's see. So at -1, my function goes from decreasing to increasing. The derivative changes from negative to positive. The derivative changing from negative to positive tells me that I have a local min. So f has a local min at x equals -1, since f prime goes from negative to positive. You could also say, or alternatively say, since f goes from increasing or from decreasing to increasing. Okay. And then we're going to have a local max. So f has a local max at x equals 1, since f prime goes from positive to negative. Okay, so a few things to notice about what I'm writing out here. Be very careful that you're saying what function and if we're talking about a derivative or anything like that. So if you say it is increasing on -1 to 1 since it is positive, I will count off points there because you're referring to two different it's. So we want to say that f is increasing since f prime is positive, or that f has a local max since f prime goes from positive to negative. So just be very careful that you're referring to the function or the derivative appropriately here. Okay, I think that this is probably enough of a video. Well, okay, I'll keep doing the next example. Sorry for that indecisiveness. I'll do the next example. If you are done with watching videos right now, feel free to save this next example for later. It points out one tiny thing that we have to be careful about, but not a huge thing. Okay, so let's see. Again, we're going to find local maxes and mins. We'll also find where this is increasing and decreasing for this function. I'm going to go ahead and distribute so that I don't have to use the product rule. So if I do x to the 1/3 times x squared, I have to add 2 plus 1/3. That's going to give me x to the 7/3 minus 4x to the 1/3. Now I can take the derivative. I get 7/3 x to the 4/3 minus 4/3 x to the -2/3. And life just got messy here. I'm going to rewrite all of this so that we can find the critical numbers. This is really kind of the messy part of this one is finding the critical numbers. But let's rewrite this as 7/3 x to the 4/3 minus 4/3 x to the 2/3. And let's go ahead and find a common denominator for these two pieces. That common denominator is going to be the 3x to the 2/3. So to get this with that denominator, I'm going to need to multiply that by x to the 2/3. So x to the 4/3 times x to the 2/3, it's going to give me x to the 6/3, which is x squared. So that's good. That's a nice handy number. So I'm going to get 7x squared minus 4/3x to the 2/3. Okay, so the first thing that I notice here is that the derivative will not exist if x is 0. So that's going to be one of my critical numbers. That's a place where the denominator is 0. So x equals 0 is one of my critical numbers. That's a little different than the other ones we've done where the derivative existed everywhere. So we need to include 0 on our sign chart. And then let's see, we need to also figure out where the numerator is 0. The numerator will be 0 when x squared is 4/7. So that when x is plus or minus, don't forget the plus and minus, square root of 4/7, which is just not a pretty number to work with, and I'm sorry for that. This ends up being plus or minus 0.76 if you round that. Okay, so this is where we'll make our sign chart for the derivative. So I'm going to include -0.76, 0, positive 0.76. Okay, and now I need to pick numbers to plug into my derivative. So let's see. Something smaller than -0.76 would be like -1. So f prime of -1. Let's see. 7 times -1 squared minus 4 is going to be positive. The denominator is also always going to be positive because we could write this as 3 times the cube root of x, that whole thing squared. So this will always actually be positive as well. If you don't trust me, plug a number in. So I'm going to get positive down here. If I plug in a number between 0 and -0.76, try something like -0.5. I'm going to get a negative number. I'm going to get another negative number, and then I'm going to get a positive number. I'm going to let you guys verify that for me so that we don't have to take a lot of time on this video to do that, but see if that makes sense. What this is going to tell us is that my function is that f is increasing on -infinity to -0 point. Put my 0 and my point in the correct place there on that interval, and then the 0.76 to infinity. My function will be decreasing on -0.76 to 0 and 0 to 0.76. I'm not including 0 as a place where my function's decreasing because this was a critical number. So my function is neither increasing nor decreasing at that critical number. Something funky is happening there. Okay. We're going to have a local max. So f has a local max at x equals -0.76, since the derivative goes from positive to negative there. We don't have a max or a min at x equals 0 because the sign of f prime does not change there. And then f will have a local min at x equals 0.76 since f prime goes from negative to positive there. Okay, let's look at this graph on Desmos just to see what happens and see if we agree with everything here. So I'm graphing my original function. Okay, so this is my original function. Okay, so it looks like indeed the function's increasing up until, yes, negative 0.76. That's good. Then it's decreasing until it gets to 0.76, and then it starts increasing again. We've got a local max and then a local min. That's good. Let's look at what's happening at x equals 0. At x equals 0, what happens is we actually have a vertical tangent line, and that's why we have a critical number there, because the vertical tangent line means the derivative does not exist, and that's what that critical number at 0 is doing. So something weird happens there indeed. Okay. So we'll get a lot more practice with this in class, and then next class we'll talk about what the second derivative tells me about the graph of my function.